Hi, I'm Professor Goins, and welcome to the Math Professor's YouTube channel. If you find the content to be useful or interesting, please consider giving our videos likes, comments, share our videos, subscribe to our channel, all those free things that are extremely beneficial to us to help spread the content and to help our channel grow. In this video, I'd like to take a look at the concept of a type 1 improper integral. What I want to do is let's consider the following specific example. Let's take a look at this region here, bounded by the graph of e to the negative x, starting at 1 and then going all the way out to the right, meaning I'm looking at this strip of area that's infinitely long. Now, it seems intuitive, or using intuition, that if this region's infinitely long and it's an area, shouldn't the area be infinite? I mean, shouldn't the area just grow and grow and grow? And it does. It keeps getting bigger and bigger because it never stops. But does it have a value? Does it have a finite value? Or is it always going to be infinite? Let's take a look. Symbolically, the value, and again, I put value in quotes here because if it's infinite, then it's not a value in our everyday sense of the word value. Of this area would be the integral from 1 to infinity, whatever that means, of e to the minus x dx. Well, remember that when we evaluate an integral, we have to plug in the upper and lower limit of integration. Certainly, we can plug in a 1 to the antiderivative, but we can't plug in infinity. It doesn't make sense. We can't have, infinity is the concept. It's not a real number, meaning I cannot evaluate with that. Well, let's see how we can kind of get around that idea. How we could sort of evaluate with infinity. Let's take this region right here and let's truncate it. In other words, let's stop it at a specific point. For example, let's just pick an arbitrary value. Let's say we go from 1 to b. This is something we can easily find the area of. It's just the integral from 1 to b of e to the minus x dx, and you can evaluate that, and you're going to get, when I plug those limits of integration in, I'm going to get an expression that has a b in it. Now, so then, what I can do is, how could I make this region become this region? Well, remember b was arbitrary, so I could say, well, if b is, just pick a random number, say it's 2, and then 3, and then 4, and then 5, well, I want b to get bigger and bigger and bigger. Naturally, that leads to the concept of a limit at infinity. In other words, I just take this area after I compute it, and then to get this original area, I take the limit as b goes to infinity. Now let's summarize that symbolically. The integral from 1 to infinity of e to the minus x dx, this original infinitely long strip here, that value of that region is given by, well, I take this integral from 1 to b, but then I take the limit as b goes to infinity. So I compute the integral first, then I take a limit of it. Let's walk through that computation. Antiderivative of e to the negative x will be minus e to the negative x, evaluated from 1 to b. Plug in my limits of integration, I'm going to get the limit as b goes to infinity of negative e to the negative b minus negative e to the negative 1. And again, I'm taking the limit as b goes to infinity. Well, e to the negative b, or more precisely in this case, negative e to the negative b, as b goes to infinity, that would be 0. So I would have 0 minus minus, so plus e to the minus 1, which gives me 1 over e. Therefore, the value of this infinitely long region is equal to the constant 1 over e. In this case, when we have an integral where it's infinitely long and it actually has a value, we refer to this as saying it is convergent. In other words, this, which is called an improper integral because one of the, type 1 improper integral because one of the limits of integration is infinite, is a finite. If it's a finite value, then we say it's convergent. On the other hand, if it did not have a finite value, we would say that it's divergent. Let's compute another couple of examples of type 1 improper integrals. Let's take a look at the integral from 0 to infinity of 1 divided by 1 plus x squared. Think about that for a couple of moments. What would the antiderivative of that be? Okay, that expression comes up pretty routinely in a calculus course, Calc 1 and Calc 2, and of course the antiderivative is the inverse tangent. Well, first and foremost, the integral from 0 to infinity of 1 over 1 plus x squared dx. First thing I have to do is I have to write this as a proper integral. In other words, the limits of integration are finite, and we'll also take a limit. So I have to write this as the limit as b goes to infinity, integral from 0 to b, 1 over 1 plus x squared dx. In other words, to evaluate in a type 1 improper integral, we have to compute an integral and a limit at infinity to be precise. Antiderivative, as I just mentioned, of 1 over 1 plus x squared to be tan inverse. So we get the limit as b goes to infinity of the inverse tangent evaluated from 0 to b, limit as b goes to infinity of tan inverse of b minus tan inverse of 0. Now tan inverse of 0, of course, is 0. What about the limit at infinity of tan inverse? Well, before I show you that, let me remind you really quickly of what the graph of the tangent function looks like. So this is y is equal to tangent of x. So remember that tangent comes in these different regions, these different sections of this repeating pattern, right? Well, if I want to have an inverse function, we have to restrict that graph so that way it passes the horizontal line test. Meaning what I do is I have to restrict tangent to be between these two vertical asymptotes, which means that the x values have to be between, well, when is the tangent undefined? Remember, tangent sine over cosine, denominator being cosine, is 0 at odd multiples of pi over 2, which means this would be 1 pi over 2, this would be negative pi over 2. So I have to restrict the graph of the tangent to be just this portion right here in order to have an inverse function. And then when we graph the inverse function, first and foremost, let's redraw this just with the restricted portion of the tangent. And then what we do, remember, is we reflect over the line y equal to x. Terrible sketch, but hopefully we get the point. So this one is the tangent function, and then when I reflect it, let's see, I'll use blue, I guess, hopefully it shows up differently on screen, that you can differentiate the two. But if I reflect it over that line, it's going to become this. And the idea is these vertical asymptotes become the horizontal asymptotes, meaning this asymptote of x equals pi over 2 becomes this horizontal asymptote of y equals pi over 2. In other words, as for the tan inverses, the input goes off to infinity, the function values get close to pi over 2. Okay, therefore this would be equal to pi over 2 minus 0, which of course is pi over 2, and therefore the value of the improper integral is a positive, or, well, is a finite real number, is a real number, and hence we say it's convergent. Let's try another one. For this example, let's take a look at the improper integral of 1 over the square root of x from 1 to infinity. Solution. First thing is a symbolic change. We're going to write this as the limit as b approaches infinity, integral from 1 to b, and, well, let's leave it alone for the moment, 1 over root x dx. So I have to change the infinite limit of integration to a limit at infinity. Okay. When I want to integrate, find an antiderivative of this, it's useful to rewrite this as x to a power. One divided by the square root of x would be x to the negative 1/2 dx. Antiderivative, add 1 to the exponent, divide by the increased exponent. Negative 1/2, if I add 1, it would be x to the 1/2. Divide by the increased exponent. Evaluate that from x equals 1 to b, giving me the limit as b approaches infinity. Now, the reciprocal of 1/2 is 2. That would be 2. And if I plug in the upper limit of integration, that would be the square root of b. Minus, plug in the lower limit of integration, 2, and then square root of 1. Of course, this term is just 2. But as b goes to infinity, the square root of b grows without bound. In other words, this is equal to infinity. And as I mentioned, if the value, so in air quotes, the value of the improper integral is not a real number, then we say it's divergent. Let's take a look at one more example. Let's look at the integral from 1 to infinity of 1 over x to the p dx, where we're going to consider p to be a real number other than 1. So p is an element of the real numbers, however, we're going to exclude the value 1. So this notation means p is an element of the real numbers, excluding 1. The idea is if p was 1, the antiderivative would be the natural log. But what I want to do is I want to essentially generalize this to figure out when is this type of an integral convergent and when is it divergent. So solution. As I mentioned, the first thing we have to do is write this as a limit at infinity. And 1 over x to the p, we can start by writing that as x to the minus p and then dx. I'll just dry that off just a tad more. Same computation as above. We're just now using a generic exponent as opposed to the fixed, negative a half. This would be the limit as b approaches infinity of x to the negative p plus 1 divided by negative p plus 1. So I divide by the increased exponent. Evaluate that from 1 to b, which gives me the limit as b approaches infinity. I plug in my upper limit of integration. I get b to the negative p plus 1 divided by negative p plus 1 minus, plug in my lower limit of integration, 1 to the minus p plus 1 over minus p plus 1. Okay, and I have to evaluate that at infinity. Clean up the side of the board, and we'll finish the computation up here. Let's clean that up a little bit before we evaluate the limit. We've got the limit as b approaches infinity. So let's see, b to the negative p plus 1. Not really much I can do with that. So let's just leave that alone. B to the negative p plus 1 over negative p plus 1. Now the second term here, of course, 1 to any power is 1. And then in my denominator, I've got negative p plus 1. So the numerator, again, is 1. Denominator is negative p plus 1, but then I'm subtracting. So what I could do is I could write your denominator. I could distribute that through to make that positive p minus 1. And then I'll rewrite it as 1 minus p. Meaning I have plus 1 over 1 minus p. Okay. Now, at this point, we have to look at the varying cases of what the p-values could be. Remember, we assumed p was not 1. So let's look at what happens if p is bigger than 1 and p is less than 1. So case 1. Let's look at p is bigger than 1. So 2, 3, 4, etc. Or any real number bigger than 1. Well, if p is bigger than 1, of course, this is just going to be a constant. This is the term we're interested in. So let's analyze this. If p is bigger than 1, that means that, look at this exponent, negative p plus 1. Just for instance, let's say p was 2. Then that would be negative 2 plus 1, which would be a negative exponent. I flip that then to the denominator to make it a positive exponent, and as b goes to infinity, that would be 0. But that's going to happen as long as negative p plus 1 is a negative number, which will happen if p is bigger than 1. If p is 1.1, negative 1.1 plus 1 would be negative 0.1. Then flip that to the bottom, and then that limit would be 0, meaning your value for case 1, your limit would equal 0 plus 1 over 1 minus p, which is 1 over 1 minus p. And then, in this case, your improper integral would be convergent. What about case 2? What if p is less than 1? P is less than 1. Again, let's pick a specific value. Let's just say 0. Just to be able to eyeball it easily. If p is 0, then this would be negative p plus 1 would be an exponent of 1. So b to the first, which is b, divided by 1, this would just be a b. And as b goes to infinity, well, b would go to infinity. So therefore, you would have a divergent integral. And of course, that's going to happen anytime this exponent here is positive, which occurs when p is less than 1. In particular, if p is 0.9, negative 0.9 plus 1 would be 0.1. b to the point 1 would go to infinity as b goes to infinity. Therefore, in this case, for case 2, you would have equal to positive infinity. And therefore, you would have a divergent integral. So let's summarize what we just found. So what we have is the integral from 1 to infinity of 1 over x to the p dx. Make it look like a piecewise function here. Well, this is equal to 1 over 1 minus p if p is bigger than 1, and it's infinity if p is less than 1. Now, this type of an integral comes up so often that we give it a specific name, and we refer to this as a p integral. Okay, this will come up frequently throughout your course, so again, we give them a specific name. So a p integral is convergent if p is bigger than 1. Not only that, but we know that we have a formula for the value, 1 over 1 minus p. In other words, if I wanted to do a quick example of what's the integral from 1 to infinity of 1 over x to the 5th, well, it'd be 1 over, and I just discovered a typo. That should be p minus 1. Let me see, let me look at that. Yep, you know what? I just discovered a typo. This should be 1 over p minus 1. I'm sorry about that. So let me highlight that in a different color here. That should be p minus 1. This should be p minus 1. This should be p minus 1. This should be p minus 1. Half tempted to redo the video, but hopefully that ends up being okay. All right, anyway. Integral from 1 to infinity of 1 over x to the 5th would be 1 over 5 minus 1, which is a quarter. And it's therefore convergent. Okay. Once again, apologies for that little typo there. Hopefully the rest of it was okay. Thank you for watching, and please don't forget to subscribe.